Welcome to your first instructional video. At this point, hopefully you guys have looked through the syllabus, you've watched that first video over like how to work Canvas, how to work Pearson, and now you're ready to learn. Well, the first thing we're going to be talking about is a concept called limits. In order to understand calculus, you have to be able to understand what a limit is. So we're going to introduce this, we're going to look at it on a graph, and we're really going to answer this question of what is a limit? Well, the definition I'll give you is as follows. A limit answers the question, what happens to a function as your x value approaches a certain number? So let's look at an example. Here we have a nice simple linear function of 2x minus 1. But what if I wanted to know what's happening to the function as I approach this value of 3? Well, to write that as a limit, I would write LIM for limit, and then under that I would write x arrow 3. And that's saying what's happening as x approaches 3. So x is approaching this value of 3. And what's happening to my function? So what's my limit of f of x? Well, what's happening? If I look at this function, right? If I approach 3, if I approach from this side, my value is getting closer and closer to this y value. And that's also true if I approach from this direction. So as I approach from that direction, same thing is happening as I'm approaching this y value. What's that y value? That y value is 5. So I would say the limit as x approaches 3 of f of x is just equal to 5. Well, guess what? That's just the corresponding y value for when x is 3, right? You can get that just by plugging in 3 to the function. 2 times 3 is 6, minus 1 is just 5. So what's the point? Why do I actually need limits when I can find that by just plugging it into the function? Well, there's actually two big reasons why limits are important. Well, there's actually two big areas where we like to use limits, where they become very helpful. So, and these two circumstances are, well, what if the x value approaches a number where the function is not continuous? We call these discontinuities. So that's what these are called. So that's where limits can be helpful, because with the discontinuity, you can't actually plug your function in. Or you can't actually plug a value into your function because a lot of the times your function's undefined at that point. And the other area where limits are important is, what if x is approaching infinity? In limit notation, that would look like this. If I let x approach infinity, what happens to my function? So limits are important here because I can't actually plug infinity into my function. So that's where limits are important. So let's look at an example now. So here we have a really fun function with lots of stuff going on. In fact, we call this a piecewise function because you can kind of split it up into pieces, and depending on which piece you're looking at, the rule is different. So the rule changes based off of what x value you're looking at. But it's all one function, where all of this is f of x. And what we're going to look at is, where might I want to look at the limit? Well, first off, where do I have discontinuities? Well, if I look at -3, we can see I've got a little open circle at -3. So that counts. That's a discontinuity. What about at -1? -1, I've got a discontinuity as well. Because if I try and plug in -1, I don't get a defined value out. And last, remember, discontinuities are places where you have to pick up your pencil. The last place I need to pick up my pencil is here at +2, right? So I have 3 discontinuities of this function. There's 3 discontinuities in this function. And let's look at each of these. Okay, let's start with x equals -3. Well, like we said earlier, this is where limits become helpful. because now I can ask the question, what's happening to my function as I get really, really close to -3? What's happening to my function? Well, if I approach from this side, I approach this y value of, I don't know, 2.7. And if I approach from this side, same thing happens. I'm approaching a y value of about 2.7. So I'd say my limit is equal to 2.7. Now, of course, that's different than what the actual function value is. If I try and plug in -3, I have an open circle there, and my function value doesn't actually exist. Well, we consider this, the name of this type of discontinuity is a hole discontinuity. Or the other word you'll hear it called is a removable discontinuity. Because it looks pretty much like a continuous function except for that open circle, except for that hole. So that open circle represents. Okay, well, let's move on to the next type of discontinuity. Let's look at what's happening at -1. Well, what is my function approaching as I approach -1? Well, if I come from the left side, my function is shooting down to -infinity as I approach -1. But if I come from the right side, my function's going up to positive infinity. Interesting. So at -1, it actually depends on what direction I come from, because I'm getting two different things. I'm getting two different types of infinity, positive infinity and negative infinity. So how do I write that? Well, it turns out I can actually denote that by using a little plus or minus sign. So I'm going to put a little plus. I'll start by putting a little plus in the top corner of -1 to show, let's approach from numbers that are more positive than -1. If it's more positive, that means I'm approaching from the right side, because the right side is more positive values. And in that case, what do we decide? If I approach from the right side, my function is approaching positive infinity. But then if I change this and change the direction, so now I'm going to approach from the negative direction. Sorry, let me mark that in red. That represents coming from the left side. My limit is different. Now I'm approaching from now my function goes to negative infinity, right? We can see that right here. As I approach from the left side, my function's shooting down to negative. Well, because, let's go back to that original question where I didn't specify a direction. Because the limit is different depending on what direction I come from, then this limit actually doesn't exist. That means if I don't specify a direction, it's impossible for me to answer that question because I don't know whether to say negative infinity or positive infinity, and I would say it doesn't exist. Well, what do we call this type of discontinuity? Well, because my limits are going to infinite values, I call this an infinite discontinuity. Okay, you'll also hear this. Oh my goodness. You'll also hear this called a vertical asymptote. Hopefully that word asymptote sounds familiar, because that's something you've probably seen before. Okay, well, we do have one more discontinuity. Take a look at the limit as x approaches 2 of my function. What's happening to the function as I let x approach 2? Well, the same thing happens where depending on what direction I approach from, my function is approaching two different things, approaching two different values. So if I come from the negative direction, if I come from numbers less than 2, which is, remember, that means I'm coming from the left, I'm approaching a y value of 3. But then if I come from the positive direction, what is my function approaching? My function approaches a value of 4. So once again, I get two different values for my limit depending on what direction I come from. Which means that if I don't specify direction, once again, if I don't specify direction, then the limit doesn't exist. This one's slightly different than the one before. We called the last one an infinite discontinuity because my limits were going to infinite values. That's not the case here. My limits actually go to finite values, but they don't go to the same value. So for that reason, we call this a jump discontinuity because the graph jumped there at 2. Now, some of you guys might be saying, wait a second, isn't there one more? Don't I have a discontinuity here at 1? Well, I actually don't because I have a closed circle there. And from either side, the function is going to the same value. So that's still, that my function still continues there even though I have a weird angle. It's still continuous there. Okay, so that takes care of my discontinuities. And as we did, we looked at the 3 different types. So there's 3 different types of discontinuities that we work with. We work with holes, infinite discontinuities, and jumps. Well, we also talked about how limits are important for what happens to the function as it approaches infinity. Another name for this is end behavior. What's happening at the end of my graphs? Well, let's take a look at my function and see if this function has end behavior. What's happening to my function as I let x approach infinity? Well, letting x approach infinity means I'm letting x get infinitely large. What's happening to my function as I let x get bigger and bigger? Well, we can kind of see that the function flattens out at this value. It flattens out at a y value of 2. So, what I would say is my limit as x approaches positive infinity of my function is equal to 2. My function approaches a y value of 2 as I let x get infinitely large. Well, let's go the other direction. What's the limit as x approaches negative infinity? It's looking this way. What's happening as my x values get infinitely negative? We can see that my graph approaches this value, 3. So in this case, my function also approaches a finite value as I go to the left direction. Okay? So this is my end behavior. You can also call this horizontal asymptotes because your graph is approaching a finite value as I let it go off to infinity. This isn't always going to be the case. There's plenty of functions where if you let x get infinitely large, the y value also gets infinitely large. So this isn't always the case, but some functions will have these horizontal asymptotes and have end behavior that I can look at with limits. So this takes care of the major concepts that you'll see here in section 1.1. What's a limit? How do I evaluate limits based off a graph? How do I approach from different directions? All that kind of stuff. So I would highly encourage you guys to go ahead and start on the homework, get through as many exercises as you can, and then if you're struggling, feel free to check out my examples video for 1.1. I'll go through a couple of the homework problems so you can kind of see some of the more tougher ones. You can see how those ones work and get some help on them if you need it. Okay? Have a great day, guys. Good luck.